Okay, we are going to be looking at Chapter 23, Electric Current, and we'll be doing ohm laws and circuits. So it's electric current and circuits. Okay, first we're going to look again at the idea of voltage and current. So current is a measure of the flow of charge in a circuit. And why will electrons flow? Why do the charges flow? Well, they flow because there is a potential difference at either end of the wire. So, for instance, why does a waterfall flow, right? It's because one part is higher and one part is lower. So the water flows from the high to the low. The same sort of thing happens with an electric circuit. Electrons flow from a point of high voltage to low voltage. So we need a potential difference or voltage difference between 2 points. Now, current is represented by the letter I, and it is measured in amperes for Mr. Ampere. Right. And so an ampere is 1 coulomb per second, because current is a measure of the flow of charge. So how many coulombs of charge pass a certain point in a second? All right. So if you were going to think about that as a little bit of current is charge per time, Q representing charge here, so I is Q over T. And so if you're looking for charge, that would be current times time. And so if you wanted to say, okay, I've got 3 amps of current, in 1 second, how much current would flow? Okay, so we've got the current, we've got the time, 3 amps times 1 second is 3 coulombs of charge. Now, if we want to say, okay, how many electrons is that? That's just charge. Well, you've got to divide the total charge by the charge per electron, which remember was E, the fundamental charge. So 3 coulombs divided by 1.6 times 10 to the minus 19 coulombs per electron gives you 1.875 times 10 to the 19th electrons. So this is a million times 18 electrons. That's a lot of electrons. Sometimes we do compare the flow of current in a circuit to the flow of water in a water circuit. So the idea is water flows from higher gravitational potential energy to lower energy. Charge flows from higher electrical potential to lower potential. Now, so we've got some water here, an upper reservoir of water and a lower reservoir of water. They're joined together, so naturally what will happen is that they eventually will reach the same level, right? Okay, to keep that from happening, to keep your waterfall flowing in your garden, you need to pump water back up. So the idea is you've got to raise those water molecules back up to the high potential energy. And for a circuit, the same sort of thing happens. You need to maintain a potential difference. You have to maintain this difference, but in terms of, instead of gravitational potential, electrical potential. So what device can maintain a potential difference in a circuit? That's where batteries come in, right? Batteries or power supplies. Okay, so we have to keep pumping it up. All right, so voltage sources like batteries maintain a potential difference. So between the ends of a battery, if we say it's a 1.5 volt battery, there's 1.5 volts of potential difference between the positive end and the negative end. And that will push the electrons around the circuit. So, of course, if you don't have batteries, if you're running it off the outlets in your house, then, of course, it's a generator or a power plant. that is maintaining that potential difference in your house of 120 volts. Okay. So the ends of an electrical conductor have to be at different electrical potentials, right? So usually if we have a 1.5 volt battery, then usually we think of one end as being at 0 and the other end being at 1.5. But it doesn't have to be that way. We can stack batteries also so that we could have one end at 2 or something, and the other end would now be 3.5, because the battery always maintains a difference of 1.5 volts. And so when this is hooked up to a circuit, charges will begin to flow in the battery, and the flow will persist until the battery no longer can maintain a potential difference. And at that point, the charges will stop flowing. So if you've ever used a flashlight and it got dimmer and dimmer and dimmer, that's what's happening inside the battery. And eventually it reaches a point where it can no longer maintain that potential difference. And then your flashlight goes dark. And batteries can be working by chemical disintegration of zinc or lead and acid. So like a car battery, you never want to play around with those because they have acid inside the chambers. And so chemical bonds can release energy as electrical energy. Rechargeable batteries have reversible chemical reactions so that you can bring the battery back up to a potential difference. Okay, so you can think of a voltage or potential as providing some sort of pressure to push the electrons through a circuit. And that does actually have a name. It's called the EMF, which isn't introduced in this book, but it's such a cool word, which is called the electromotive force. So the electromotive force, the EMF, okay, it provides motivation to push those electrons along. And here you see this car battery, a 12-volt car battery, has a potential difference between its two terminals. If I put a wire on that, notice also that there is an electric field around the battery that you don't usually sense. And when I put a wire on it, how the electric field is now inside the wire, and that provides the electromotive force to push the electrons through the wire. Now remember, the electrons are in the wire already. So unlike a tube with water, which can be empty, the wire is never empty. It always has electrons in it. Okay, so electric current is the flow of electric charge. In a metal, it's conduction electrons. In fluids, it could be positive and negative ions. So like an acid, HCO3 usually breaks up. You can have the H positive flowing as well as the CO3 negative charge. Okay, so anyway, so you can have positive or negative ions flowing that can conduct electricity. And 1 ampere is the flow of 1 coulomb of charge per second, which is around 6.25 billion electrons per second. Now, electrons, we tend to think, oh, this is fast, right? Electrons must be zooming through those wires. Well, it turns out the speed of the electrons is slow, but the electric signal, or the EMF, travels near the speed of light. So one individual electron tends to bounce around and what's called the drift velocity. So this electron will eventually reach that location, but first it's going to go back and forth, and it's going to zip around from place to place. And eventually, because it keeps getting captured by molecules, so it bounces from atom to atom, molecule to molecule, eventually it moves forward in the direction you expect. But that takes time. And the drift velocity is only 0.01 centimeters per second. So it takes about 3 hours just to go 1 meter. Okay, so think how horrible it would be if you turned on a light switch and then it took 3 hours for the electricity to ooze up to the light bulb. Okay, but that's not what happens. Remember, all the electrons are already in the light bulb and in the wire. So all you have to do is start them moving. And so the electromotive force, the push, starts right away. All the electrons start moving pretty much at the same time. There's no waiting for it to actually go from the turn on switch to the light bulb. So we don't have to wait for our electricity. It happens right away, very quickly. Okay, now current can be divided into direct current and alternating current. Direct current is what you know as DC, of course. Alternating current is AC. Direct current, the electrons are always going in the same direction. And so this is what we have in batteries. So of course we use it in automobile batteries usually. And any other thing like your cell phone or your laptop, those would use direct current. But your desktop computer is probably using AC, alternating current. And so this is what we usually use in homes. And the electricity is going back and forth and back and forth. Now, this may sound like it's not getting anywhere, but it works perfectly well. Because one of the main things that the electricity does, well, in a light bulb anyway, an incandescent light bulb, is it creates friction to create heat. And so remember, when you're rubbing your hands to create heat, you don't just go in one direction, right? Instead, you rub back and forth and back and forth. And so the idea is that, yeah, you can create friction either way. And so back and forth works for that, for friction purposes. It also works for a lot of other purposes because we build motors that run, that are attuned to that back and forth motion, which we'll discuss in 2 more chapters, chapter 24, 25, one of those. Okay, so anyway, so in homes we use a 60 cycles per second frequency. So the electrons are moving back and forth, they're changing direction 60 times per second. The voltage in a household is usually listed as 120 for us science folks. Electricians sometimes number at 110. There are various historical and mechanical reasons for that. But anyway, so your homework problems, you're going to use 120 for most homework problems that involve household current. Yep. So if we look at it here, we've got direct current would maintain, if it was 1 amp, it would maintain 1 amp in the same direction the whole time. If it's alternating, then the current would be large and going in one direction, and then it would go to 0, and then it would be going the other direction. Okay, so it would be in the negative direction. And this would repeat over and over again. So sometimes in an alternating current, the current is momentarily 0 because the electrons are busy switching direction. And this happens in an electric generator. When we talk about AC generator, we'll talk about how easy it is to make alternating current. It's very, very simple. And that's one reason that we use it. Now, alternating current can be converted to DC current using what's called a rectifier, which uses a diode. And a diode basically will only accept electricity in one direction. So when you put this alternating current through a diode, it ends up looking something like this. It's only chopped off the positive parts of the current in one direction. But if you use a second diode to capture the parts that are here, then later you can flip those around, add them back in, and end up with something that looks like this. Something that's approximately DC. So you have changed your AC into DC using diodes. Now, do you do this very often? Yeah, you do this a lot. Every time you're plugging in your charger for your cell phone or your pad or your, for your computer, this little box here, that contains rectification, okay? So there's some diodes in there that are rectifying the circuit. Okay, so that has to happen because your laptop has a battery that needs to be charged with DC, but the wall produces AC. So what we do is that has to be rectified. And let me get this charger back in. All right. And these are diodes, LEDs, which are now the best thing to use for light bulbs. Okay, so LEDs. Now, it used to be they didn't know how exactly to make really an LED light bulb exactly because our house does use alternating current. And LEDs basically run off DCs. But they figured it out. So we now have LED light bulbs that are working fantastically and saving lots of energy. So make sure you put in your LEDs. Okay, now electrical resistance we've talked about before. Resistance is the resistance to the flow of current. And most materials do have some resistance unless they're superconductors. It's represented by the symbol R. It's measured in ohms, as we talked about before. And so if you're thinking about a water system, that might be where the hose has some kinks or something in it. So that slows the water down. And in a circuit, a resistor is represented by a zigzag line. So here's showing a circuit and relating that to a water wheel idea. And we've got the circuit here. So the conventional notation for a circuit diagram, let me redraw the one that's here because it's kind of sad. A battery is represented by two parallel lines. The longer side represents the positive side of the battery. Switch can be represented by two dots to show this is a switch that can open. Resistor. Okay. And by convention, current comes out of the positive end of the battery, so that would be where I is going. But there's a little problem. It turns out that current was defined, the direction of current was defined by Benjamin Franklin. And he wasn't sure if the positive charges or the negative charges were flowing in a wire. So he took a guess. He said, let's assume it's the positive charges. And then after that, for the last 200 years, we have all been kind of stuck with the idea that it's the positive charges that move, even though we now know it's the negative charges. But then you didn't have to deal with negative numbers, and so we just pretend that the current is a flow of positive charge. However, in reality, the electron flow is in the opposite direction. The electrons actually flow out of the negative end of the battery, around the circuit, and back in the positive end. Okay, so it's a little bit weird, but the electrons go opposite the actual direction of the current, or the defined direction of current. Okay, now when that electricity goes through a light bulb, of course it goes in through the filament and back out. Okay, so it's always got to go in a circuit. A circuit is like a circle. It's got to make a complete circuit. And along the way it does some work. This one produces heat and light. And here the water wheel is doing work, or has work done on it. Okay, and here's just some cute pictures of resistors. In the lab, we're going to be looking at some resistors like these. They have color-coded bands, which you're going to learn the color code. This is a potentiometer. It's a small resistor that you can use. So like these are like the size of lentils or beans. So this is only the size of part of your finger. But anyway, it's you can twist the handle and change the potential. Oh, I've got to find my variable resistor. Okay, all right. See you in a few minutes. We're going to look at part 2.